This is the third lecture of Computer Science 47, section 01. We'll be talking about number representations in this class, and our specific topics will be integer representation, then format conversion between different integer forms, and negative integer representation in computing systems. Now, to start with the integer representation, we can say that there are multiple different number system and it has their specific applications. So as human beings, we all understand and used to this number system like decimal number system, which uses 10 symbols 0, 1, 2, 3, etc. till 9, and all the decimal numbers are represented with those 10 symbols, and that's why it's of base 10. Whereas the binary number system, which uses only two symbols 0 and 1 to represent any number in the whole world, okay, and that's of base 2 because it uses only two symbols. This binary number system has been adopted into computing system, especially electronics computing system, because in electrical world it is very easy to represent 0 and 1 by two different electrical state, on for 1 and off for 0, for example, let's say, right? So that's why the binary number system is the number system which is used any modern electronic computing systems. There are other number system like octal, which uses 8 symbols 0 to 7, which is of base 8, and hexadecimal number system, which uses like 16 symbols 0 to 9 like decimal, and then letter A to F, A, B, C, D, E, F. That's the total 16 symbol, and it is of base 16. Use of them, especially hexadecimal, it's to represent a value which is represented in a binary form, which you will see it can take a huge number of symbols to represent certain value. Hexadecimal number system compacts that representation of a value into very short string, I would say, a short series of symbols, okay. And from binary to hexadecimal, in successive slides we'll see conversion is very easy and very fast, and we can just represent a huge binary values with multiple symbols in it, can be represented in a very compact form using hexadecimal system. Additional note, a binary number system, when we talk about this symbol, we also name popularly as bit, okay. Bit stands for binary digit, all right. So bit stands for binary digit. They are basically these two symbols 0 and 1, and this is represented in electrical system as a electrical off and electrical on state. From mathematics point of view, this number system is of base 2 because there are two symbols. We use hexadecimal to represent the same value as represented in the binary in a much more compact form with using 16 symbols. Now about the octal. Octal is interesting number system. There were one time when I think from IBM there was a machine which is 24-bit system, and for that people used to compact the binary numbers into octal for further representation of the values and stuff like that, for compaction purpose. But nowadays it's kind of more academic. Just to know, as a general knowledge, there is an octal system which uses like 10 symbols. In fact, we can derive many number system as we want. These are like more known popular number system. We can make up our own custom number system, and the symbols may not be just 0, 1, 2, 3. You can use anything as a symbol like alpha, beta, gamma, theta, or anything like that. Whatever symbol you can come up with, right? Hieroglyphics, anything, right? Anything you can think of. And you can also say that I'm going to represent any value in the world, let's say, with 3 symbols. That's a valid number system with a base 3. Or I'm going to represent a number system using, let's say, 7 symbols, base 7, right? That's also a valid number system. Okay, so we can construct, we can make any number system with any number of symbols. We can define our own symbols, so on and so forth, and we can do maths with them, and etc, etc. But for our purpose, we'll be concentrating on decimal for obvious reason, because we are human and we can perceive values through the decimal system more clearly and obviously than like binary, octal, or hexadecimal. We'll learn the binary because in the modern computing system, that is the way to represent a number, and electronic system understand this system of representation of values, whereas octal is an archaic old number representation system. Sometimes back it used to be used in the IBM, some of the IBM 24-bit system to compact some representation of values from binary into octal easily. Nowadays, hexadecimal is that alternative of compaction, mostly because computing systems are 32 or 64 bit, so it makes sense to compact a value represented in the binary with much compact representation as an hexadecimal number system. However, just to note, inside computing system, every value is represented with binary, on and off states. Series of on and off composes a value, represents a value. Computing system doesn't care about decimal, doesn't care about octal, doesn't care about hexadecimal. These are all for human. Decimal, octal, hexadecimal, all for human use purpose. Binary is the only number system that goes into modern computing systems. Now, in this context of math, using multiple number system, especially when you're dealing with different number representation and solving problems around that, a base value, writing a base value associating with a representation of numbers is very important. Because, for example, like if we write 1, 0, and see these 2 symbols are present in all these 4 different number systems. Decimal has 0, 1, binary has 0, 1, octal has 0, 1, hexadecimal has 0, 1. So just writing 1 and 0, it doesn't convey you the sense of value directly. If you say it's a base 10, okay, that's a 10, we all understand. If you say it is in base 2, then it's a different, it's not 10, the value 10 anymore. It is basically, its value is 2. Okay, 1, 0 is 2. We'll see that. And similarly for the octal and this hexadecimal, it represents different value, different quantity, because its base is different. So bottom line is that if we are dealing with different number systems, then it is a good practice, it is a good habit, and sometimes it is mandatory to represent and write its base of the number system value. Okay. So now conversion from to and from decimal into an arbitrary number system, let's say base n. Okay. This is important because we are human. We all deal with decimal numbers representation, so that the value we can sense the value, we can perceive the value. That's why we'll need to learn this. Okay, we'll be dealing around with the decimal to and from, converting to maybe octal, maybe binary, maybe hexadecimal, and maybe any arbitrary system with n number of symbols. All right. So the formula to translate a n-digit number in base k into corresponding decimal value. Okay, so here the important part is that it's a n-digit number, means my value is represented with n symbols. Okay, string of n symbols with a base k number system, means there are k different type of symbols available into the system. I want to transform that into a decimal value. Let's say these individual n symbols, string of symbols we write down for the value, let's say they are called di for the ith position of that value string. Then assuming 0 is the rightmost digit, okay, so index 0 is the rightmost digit in that n symbol string, our value represented in decimal number system, this is base 10. To do that, what we need to do, we need to go through all the symbols from 0 to n minus 1, means all the n symbols indexed by from 0 to n minus 1, multiplied with base value, let's say that is of base 7 for example, okay, or base 16 like hexadecimal, with that base to the power I, and we add up all of them. So this is the formula is going to be used. Please remember this is a sigma of I from 0 to n minus 1. You multiply each symbol value, okay, symbol has to have a corresponding decimal value, and that is already defined by the number system, by the way. We'll see that, and we take that value of that symbol at a position I, multiply by base value to the power I. If we sum them up, we get a value in the decimal number system. What is the corresponding conversion, reverse conversion? Let's say I have a decimal value, I want to convert it into a number system with base k. All right. So again, this target number system, we need to know the base value, which is how many symbols are there, and what is the decimal values of each of these symbol in the target number system. That's what we need to know, right? For example, hexadecimal number system, let's say 0 to 9 has a corresponding decimal values as it is, like 0 is 0, 1 is 1, 2 is 2, etc. Now after that, A, B, C, D, E, F, this 6 symbol has a corresponding decimal value of 11, 12, 13, 14 and 15. All right. So these are the value for the decimal value for the symbol that we need to know also for the target number system which we want to convert. Once we know that, then we run this little algorithm. What we do, we take the decimal value, we do a modulus operation with base k. Okay, so this means we are kind of computing the remainder from the division operation, and also we are computing the quotient of the division operation. Now the remainder we are assigning to a different variable where num is updated with the quotient from that division. Okay, that is the integer division. And let's say we initialize an index to 0, then my digit at that 0th position is your remainder. Okay, 0th position is your remainder, and you are increasing the index by 1. And how long you will be in the repetition loop? Till your number is not equal 0. It's like, see, at this second line, okay, this line, we are assigning quotient of num by k into the num, so that will be kind of diminishing in each step, and ultimately it will result to 0. So it's not an unbound problem, it's a bound problem. So your program will come out of the loop, and each step we are computing the remainder of that division and putting that and inserting that into the digit sequence. Let's say that's an array of symbols, or whatever we are trying to do. We are inserting them as the remainder values. So let's say we are converting to the hex, and my remainder become like 12, right? So I know I'm talking about the symbol B there. Okay, if its remainder is 3, we're talking about a hexadecimal symbol 3. And if it is a remainder is of like 14, then we are talking of an hexadecimal symbol E, something like that. Okay,